So now that they are in, welcome back everybody. Maybe some of you attended Sean's talk yesterday, then you could also see this beautiful robot there. For those who weren't there, I can tell you it's not only standing there, but it's also nicely walking. And now Sean will tell us everything what this is all about. Please join me in welcoming Mr. Sean Harmer.
Thank you. Welcome everyone. And as you can see, today's talk will involve some robots. So let's get started about how we can use animations with Qt 3D. So the structure of today's talk is going to be a very quick overview about animations in general and specifically animations in Qt 3D. And then we'll have a look at how to actually apply some simple animations into your applications. Oops, and I've clicked on something already. Once we've done that, we'll knock it up a notch and have a look at these things called skeletal animations, which have a slight air of mystery around them. But we'll explain it all. It's actually pretty simple when you boil it down. It's just lots and lots of data. And then towards the end, we'll have a look at the concept of blended animations and why we want these things. And once we understand why we want them, how we can actually achieve them with Qt 3D. And then finally, we'll finish off with a little bit of a clue as to what's coming in the future around animations. But before I go any further, I'd like to give full credit to a couple of my colleagues, Johan, who's sitting in the front row there. Thank you, Johan. And also Timo. And also Timo, who's not here this week, but who was invaluable in producing all the data used in these examples, which I'll show today. So first of all, why are we actually doing this? We can already do animations inside Qt. We've got Qt property animation, we've got Qt graphics view, and we've got more recently the Qt quick animations that can animate properties as well. So why bother? Well, all those things are great, but they're all targeted at developers. Now, if you're like me, which I suspect most of you are, is that developers actually suck at making animations. Yep. Just like we suck at drawing, you've heard of developer art. Well, developer art also extends to developer animations. So I guess all of you have tried making a few bouncing animations with Qt Quick, and that's great as far as it goes, but it doesn't cut the mustard when you want to do proper professional level animations. So we also want to extend Qt to be accessible to content creators as well as developers. Now, that's very difficult with the existing animation frameworks because it's all around using the APIs to build up structures which represent your animations. There's no way for an artist to go off and create an animation in one of their familiar tools and get it into your Qt Quick application easily. So developers are not great at creating complex content. Conversely, artists are not great at software development, so how about we just let each do the bit that they're good at, and somewhere in between, we can actually help them join the dots to make something nice. Another reason we want to do this is scalability. Yes, Qt Quick has the nice render thread where we can offload all the rendering to, and the batching and everything, and recently they've also introduced the Qt Quick animator types, which also allow you to offload some of the animation onto the render thread as well. That's fine for Qt Quick and 2D work, but with 3D, often we're dealing with a whole nother scale of problem. Okay, when we get onto skeletal animations, you'll see it's not uncommon for a skeleton to contain well over 100 joints. And we may well have many of these things on the screen at the same time, all doing their own animations. So we need something that scales up better than just having the main thread do all the work, or even the render thread in Qt Quick doing all the work. So the complex animations can consume lots and lots of data. And we need to process all that data. We need to do lots of interpolations. We need to do lots of blending. There's quite a lot going on behind the scenes. Now, it just so happens that Qt 3D scales very well up to multiple cores. In fact, as many cores as you throw at it, Qt 3D will consume. It makes many more jobs than what there are cores. And the nice thing about the animation framework in Qt 3D is it's completely non-blocking on the main thread. You use the main thread to set everything up, specify the relationships and the animations and what the animations should map onto. You tell it to go, and everything else happens on the thread pool behind the scenes. One slight gotcha that people run into with the Qt Quick animator objects is the fact that you only get the property updates when the animation actually finishes. This is contrary to the standard Qt Quick animations and Qt property animation, where you get every single property update. So they're the kind of two extremes. With Qt 3D, we provide you the option to opt in to property updates. So a lot of the times you just want an animation to play and let the back end get on with it. You don't care about the actual individual property values, but sometimes you do. And when you do, you can now actually get your hands on them. So this is just a new property on the Qt node class, where you can basically specify which properties you wish to receive updates for the intermediate values. Okay, so fundamentally, what is animation? It's basically just a sequence of still frames. Yeah? But if we display them rapidly enough, it fools our primitive little monkey brains into thinking that something's actually moving in between. Our brain kind of fills in the gaps, doing a sense of sort of interpolation internally. Traditional animators draw every single frame out. So if we're using keyframed animations, we know that computers are very good at maths. We have our animators specify a few positions at certain key points in time, or key frames, and then in between those times, we ask the computer to basically interpolate in between. Yep, everyone's happy with the concept of keyframes. So here we can just see a few keyframes from a simple bouncing ball example, which I'll show you a bit more in detail shortly. Now, there's a big difference between offline animation used in movies and TV programs compared to what we need to do in real time. When we're doing offline rendering, the animator and the technical directors all know the exact time each frame will be rendered at the screen. And they can exactly script the animation to take that into account. When we're doing real-time rendering, we have to deal with these pesky things called users and also data coming into the system that may completely change the way our animations play out. So they may change the start time, they may change the playback speed, they may interact with other objects in the scene, which triggers a different animation to be played partway through. It becomes a lot more complex. So there's random variations in timing. There's also variations in timing that come from the fact that we're running on a whole raft of different hardware targets. So I've got a reasonably powerful laptop here. Other people may be running on a Raspberry Pi. We still need the same animations to work on all those platforms and everything in between. And as I said, they can also be interactive. So we have to take that into account. Now, what does that mean in practice? Well, when we're offline rendering, the animator can use their tools and they can set the keyframes at specific points, exactly on the frame times. So for example, here we see these little yellow boxes. They're some of the keyframes that have been set, and the intermediate gaps in the lines are the actual keyframes for the intermediate frames. So that artist doesn't have to set them at every single frame. They set them at specific points in time, and then the computer interpolates in between. But the point is, the artist can control these interpolation angles and things to make sure that these intermediate points line up exactly on the frame boundaries where they wish them to. And with offline rendering, it's quite common that an animation will be authored and used just once for a specific scene in a specific movie or something. Now, contrasting that to real-time animation, we need to be able to calculate the position or any other property at any point in time, not just on the frame boundaries. Because our frame boundaries may not correspond to the frame boundaries that the animator came up with when they were authoring the clip in the first place. Our animations ideally should also be reusable, so we can reuse them in multiple situations. And even better, they should be composable, so that we can join them together, we can blend them, we can play them back to back, we can interpolate from one to the other to transition. So we want to break down our animations into small, reusable clips that we can combine any way we wish. But before we can get that far, let's worry about interpolation. So I guess everyone in the room is familiar with the concept of linear interpolation. We have a couple of points, and then we basically work out the straight line in between them, and as a function of time, we can work out our position along that straight line. It's pretty simple stuff. Now, so we have simple maths in that case, but we end up with lots and lots of data. Yep, because you have to have enough keyframes to accurately represent your ideal animation curve without the linearity becoming a bit of a jarring effect when you actually play it back. So you have to finally subdivide these animation curves. So that's one option. Another option is we work with higher order primitives. In this case, we've got cubic Bezier curves. As you can see, this is just a screenshot from Blender. And basically, the animator can come in and they can create a keyframe, and then it can use these handles to adjust the shape of the curve either side and how it interpolates in between. So the nice thing about that is we have far less data to store. We don't need anywhere near as many keyframes as we would if we were using linear interpolation, but the downside is the math gets more complicated. The good news is we've done all that hard math for you, so you don't have to worry about it. So the workflow of this is your artist, your animator, will author some animations using higher level primitives. It might even come out of a physical simulation, depending on what you're trying to animate. And then you will condition that data somehow. You might decide to resample it, so you're using linear interpolation at runtime, or you might package it in a nice, convenient binary format. That's your call to make. So we process it through a nice runtime format. Or we can export curves. And then finally, you need an application that consumes that data and does something with it. And that's what the subject of this talk is about. But first, let's just have a quick look at a typical authoring exercise. So here we have one I made earlier. So this is just a simple bouncing ball. Okay, and if I play the animation, Alt-A, you can see it bouncing up and down, and it kind of simulates how you'd expect a bouncing ball to behave under the influence of gravity. Yeah, I've not included air resistance or anything funky like that. It's just bouncing forever. So down the bottom here, you can see we have a F-curve, or function curve as is known, which basically represents how that property behaves as a function of time. So as I scrub through the animation, you can see the ball starts to move down, and the spacing of the keyframes there is such that it takes small steps to start with, and then as it gets really going under the gravity, we take bigger and bigger steps, and notice the biggest step is the one just before it hits the ground. And as it comes back up again, it's symmetric, so it goes back to the same place after the bounce. So there's actually only one frame on the ground here. So if we adjust these handles, for example, we can grab that, you can completely change how this behaves. So I could stretch it into stupid shapes. Let me get rid of that. So if I move it right in there and then play the animation, it doesn't look right. Yeah, it's not bouncing correctly. So this is where the skill of the animator comes in, is to shape those curves correctly. Now, I'm not an animator. This is just something I can knock together relatively quickly. But with a bit of practice, you can get it looking reasonably good, like an actual bounce. And you might think, well, why don't you simulate with a physics engine or something? It's like, well, maybe I just want it to bounce forever. I don't want it to decay and lose energy on every single bounce. So there's reasons for doing this the old-fashioned way. I say old-fashioned, this is still using computers. We're not drawing it by hand. But the nice thing is, once you are doing this by hand, you have full control of what the animation looks like. So the artists are able to use their familiar tools. In this case, I was using Blender, which is also what Johan used. Other people use Maya or 3D Max or whatever. And this allows us to use data rather than forcing programmer art down people's necks. Now, you may not think that's a particularly big deal, but if people want professional-looking animations, it is a big deal. Because when you're doing this with a professional animator, they'll put in all kinds of niceties you probably don't even think about when you're watching an animation in a big production film, but then when you try your own, it kind of looks a bit sucky and you're not quite sure why. So some of the reasons for this are things like squash and stretch. Okay, with that bouncing ball, it was completely rigid, but normally when you were animating it properly, as it is falling down, you would stretch it in a vertical sense. As it hits the ground, you would squash it down, and then as it rebounds, it stretches vertically again. Yeah? Anticipation. People don't like it when things suddenly start to move. Okay, if you want something to take a big jump, then quite often they're going to take a bit of a step back before they leap forwards. Yeah. This is, again, something you can put in with an animation created in a digital content creation tool rather than something that, as a developer, you would have to try and code up. This is not your area of expertise. Let the animators do it. You can put in plenty of variations, and you can do things like also having, when a ball is rolling along and it comes to a stop, it just doesn't stop dead, it rolls back a little bit because of the inertia and the physics going on inside the rubber ball. So just tiny little things, but they make a difference. So we know how to make animations and some of the things that an animator might put in addition to the things that we would do as developers. Let's have a look at runtime. So there's 3 concepts we have to worry about when we're dealing with consuming animations. The first one is the animation data. So we know how to get that. We can have our artists create it in a tool and export it in a convenient format for us. We'll talk more about the formats later. We then need to be able to have the animation played back somehow, and we're going to see that very shortly. That, however, is not enough. All we do when we get an animation played back is we get a whole bunch of numbers come out. That's not much use to us. What we want to do is target those numbers onto properties of objects. That's where the real value of it comes from. So we have these 3 concepts. Now, unfortunately, the animations inside Qt Quick and, well, Qt Quick 2, they conflate all 3 of those concepts. They are all combined in the same data structures in the Qt Quick animations. So if you make a Qt Quick animation, it might be quite a complex one with lots of sequential and parallel animations in there. You have to specify the properties you want to target it to, and you're specifying the from and the to values. Okay, that's conflating the targets for the animation and also the animation data along with the playback. So Qt 3D separates these things out so we have optimum options for reuse and flexibility and also efficiency. So how do we go about this in practice? Well, to get our animation data into our application, we have to use this guy called Animation Clip Loader. Well, we don't have to, it's one option. This is actually pretty easy to use. We export our data, our animation, from Blender or whatever in a standard format. Now, one of the standard formats we're supporting is GLTF2, which is a Chronos-specified open format. Highly recommended you to have a look into it. It's rapidly becoming the JPEG or PNG of 3D content. And in Qt 3D, we're aiming to have full support of GLTF2, hopefully with 5.10. Okay, so we have some data in a file. We use our animation clip loader, we set the source URL, it loads in the animation data. So far, so good. What if you want to get your data not from a baked file on disk, but from your application or some other data source? Well, we also provide an API for this. This is called Animation Clip. This allows you to specify the data inside the clip yourself. This is very useful if it's coming from some physical simulation or something else of that nature. In that case, we specify animation clip, and then it has a clip data property where you can then call back to a C++ function to populate the actual contents of that. We don't have a QML JavaScript API for populating that piece of data yet. I'm hoping that will come in 5.11. But to be honest, if you're dealing with large amounts of data, you probably shouldn't be doing that in JavaScript anyway. Now, the contents of this clip data is structured something like this. So inside the animation clip, we have a QAnimation clip data, and that consists of a vector of Q channels. Now, a channel holds the animation data for one particular property, for example. So it might be the position, or it might be the temperature of something, or it might be the rotation angle or the color. You get the idea. Now, within the channel, there are an array of Q channel components. So these are the individual components of the position or the color or the rotation or whatever. So the red, green, blue, the X, Y, Z, the W, X, Y, Z for a quaternion. And then within the Q channel components, there is a vector of Q keyframes. And the keyframe contains the time of the keyframe in seconds and also the keyframe value. That's the minimum requirements for a Qt keyframe. It has several interpolation modes it can use. The first one is linear, which does the straightforward linear interpolation. There's also the constant or stepped interpolation, where it holds a value until the next one comes along and then it immediately steps to it. And then there's also the cubic Bezier interpolation as well, exactly as we saw it in Blender before. So in which case, the keyframe consists of the timestamp, the keyframe value, and the positions of those control handles. And with that information, that's enough to interpolate quite nicely. So the next concept was the animation playback. And this is achieved really easily with Clip Animator. So Clip Animator is a component you can aggregate onto a Qt 3D entity. You feed it an animation clip in the clip property, and it has a running property you can set to true or false. Pretty easy. So that gets us 2/3 of the way. Oh yeah, there's also more advanced options for playing back animations, which we'll talk about a bit later. So the third concept is, how do we target that animation onto some objects and their properties? Well, animations are reusable. We can use them across all kinds of objects and properties. Just because an animation channel is called position doesn't mean we have to use it as a position. We can target it to anything we like. And we can do this mapping with a pair of types called channel mapper and channel mapping. So a channel mapper contains a vector of channel mappings, and it looks something like that. So inside of our animation data, there will be a channel called, say, location, and then we can specify the target for this is going to be a transform component, which is instantiated somewhere else, and then the property on that we want to affect is called translation. And you can specify as many mappings as you like. You can even map one channel onto multiple properties of objects. It's really quite flexible. You can even activate callbacks and things using these channel mappings. It's quite nice. So let's take a look at an actual example of this, using our familiar bouncing balls. Right, so here we have 3 different kinds of balls being animated. We've got the blue one, which is doing our vanilla up and down bounce that we saw earlier in Blender. That's just been exported to a GLTF file. The red one is just doing a simple rolling ball animation along. And if you look carefully, right at the end, it does a tiny little rollback as well. So that sort of thing would be a pain to do in regular animation APIs that we have in Qt so far. And then the yellow one is just doing arcing bounce, where it loses a bit of energy each time and it's rotating as it goes along as well. But the actual contents of that is all decided by the animator, the person that authors the clips. The way we play it back is exactly the same. So here we have our scene, which is everything we just saw. So we have an animated entity. And if I go into the animated entity, that's where the interesting stuff is. We have an entity, and then the components it aggregates is just a transform, a mesh, and a material, as usual. And then we are also aggregating one of our clip animator components. We're setting the running property to true, the loops to animator infinite. We specify the animation clip using an animation clip loader, and then we have some mappings that map onto the properties of the transform component of that ball. And that's all you have to do to get in any animation into that system. So the key thing is that the animator, your actual in-person animator, is the one that determines what it actually looks like. You're just doing the plumbing here. Unless you decide not to use the animation clip loader and specify the data yourselves. But again, that's your decision as a developer, and depends what you want to achieve. So, now we know a bit about basic animations, let's increase the complexity a bit and have a talk about skeletal animations. So, as the name suggests, this involves some form of a skeleton. And on the right-hand side here, you can see a little block man in the style of Minecraft I've knocked together. And he's made up of 1, 2, 3, 4, 5, 6 cubes. Okay, so there's one for the body, one for each leg, one for each arm, and a head. And as well as that, we create a little skeleton, which are those octahedron shapes in there, and we join them together in a hierarchy. Now, so far, I've been dealing with rigid body transforms, where we animate something, the whole object moves. Skeletal animations allow us to actually make our objects bend and flex. They don't have to. It depends how you structure your skeleton and map the vertices onto it, but they can. So just to show what I mean about as limitations on how alive you can make objects feel, there's another small example, which is one I did for a quick blog post at Easter. Where's it gone? Baked keyframe animation, this one. So this animation clip is not using skeletal animation. All this animation clip is doing is it's altering the position, the scale, and the rotation of this little egg character. And with that, you can kind of see, yes, he's scaling and stretching a bit, but it's all at the object level. There's not individual bits of him flexing. Okay, so that's about as far as you can go with standard animations, not skeletal animations. Now, as I say, skeletons can deform a mesh, like living creatures, so biological things, humanoids, things like that, but it doesn't have to. We can also animate rigid bodies. If you set up your skeleton such that a joint is associated solely with one group of vertices, then you can use that as a rigid body sub-mesh of your overall mesh. But before we animate these skeletons, we first of all have to know how to render them. So let's have a look at the process involved. Now, when we make these little characters, it's not enough to create the mesh itself and the skeleton. We somehow have to associate the skeleton with the mesh. And the way this is often done is with weight painting. So here you can see a screenshot of Blender where I've gone into weight painting mode, and this bone here is selected. Now, everywhere it's colored in red, that means that vertex is 100% controlled by this bone. Where it goes into other colors, so orange and green, and then back to blue, it means those vertices are not affected at all if they're blue, and for the intermediate colors, it means they have some intermediate weight, how that bone affects them. And we do that for all the bones and all the vertices in the mesh, and that basically binds the mesh to our skeleton. And then as we move the skeleton, the mesh moves along with it. There we go. So if we come in here, so I've got this joint selected, and if I were to rotate this one around the x-axis, you can see, yep, the whole arm moves. And because the lower arm bone is parented to the upper arm bone, it moves with it. Whereas if I were to select the lower arm one and rotate that, only the bottom half of the arm actually rotates. So when your artist assigns weights for the vertices to the bones, that's controlling how the mesh deforms as the bones move. So yep, the artist, he creates the mesh, creates a skeleton, and then he binds the vertices onto the mesh. Now usually we impose a limit of 4 bones being able to influence any vertex in our mesh. You can see a big difference between 1, 2, 3, and 4 bones, but any more than 4 bones, the human brain and eye can't really distinguish it. And it's also convenient because this allows us to fit things nicely into an even number of bytes. And then there you can see grayed out as well that later on the artist also creates keyframed poses for our skeleton. So just as we managed to keyframe properties of our whole object earlier, you can also keyframe the positions of each of those joints in our skeleton individually as well. And that's what gets exported as the animation data. So inside the animation data now, as well as the times and positions inside the channels also are marked up with a joint index that allows us to correspond an animation channel onto a joint inside of our skeleton. Now, in the literature, you'll find they often refer to joints and they refer to bones. They're actually the same thing. However, content creation tools often show bones kind of as you would expect to see them, as like an octahedral shape like this, but technically joint is the more correct term. Now a joint, or a bone, they're not physical bones like we have in the human body, they are actually just a set of nested coordinate systems. So you could visualize these as just a set of axes at each of the joint positions. And just like with our usual parent-child transforms, the joints also inherit the transforms of their parents as well. Now, how do we draw when we have joints or bones and vertices as well? Well, it gets a little bit interesting. We have to do something that's called creating a skinning matrix. So let's imagine we start off with a joint, which we'll call B in this case. That's a little green circle. Well, the joint is called J, the transform is called B. This transform is called like the bind pose. So this is the pose that we set up inside of our application when we bind the mesh to our skeleton, hence the bind pose. Now in joint space, we may have a vertex in our mesh at that position there, say at 4, 3. Now what we want to do is when we transform our joint into a new position, we kind of want our vertex to move along with it. And the way we do that is, well, first of all, here's our current pose of our joint, so C for current pose. We take the inverse of our bind pose transform, the bind pose matrix, and we multiply the inverse of that by our vertex. That transforms it from joint space into global space or model space, for those of you who have done our OpenGL training. Right, so now we have our vertex in global space. That's fine. We can now multiply it by the transform for our other joint to get it back into joint space, but relative to our transformed joint. And when we do that, we find it ends up over there. And the invariant here is actually that the coordinates in joint space always stay the same. So when we're creating a skinning matrix, which is the combination of the inverse bind matrix multiplied by the current pose matrix, we find that the coordinates of the vertex in joint space are actually invariant. So all we're doing is we're transforming from joint space to global space and then back to joint space again. So that combination of matrices is not actually a change of basis, it's just applying this skinning operation. Now, unfortunately, drawing a single vertex with a single joint is not particularly common. What we want to do is draw many thousands of vertices with potentially many hundreds of bones, with weights associated with them as well. Now, the good news is the mass is exactly the same, we just have to do lots of it. The slight gotcha is that we store the joint poses as local transforms relative to their parent. So before we can calculate the skinning matrix, we need to compose the local transform with the transform of its parent and its grandparent and its great-grandparent all the way up to the root of our entity. So that gives us our global pose matrix. Now luckily, the inverse bind matrix never changes. This is constant throughout the entire life of the application, so we can just store that as a constant somewhere. Now we get the best performance not by having a hierarchical representation of our skeleton in memory, we actually linearize it. So we end up with a simple vector of transforms. And that makes it very nice and easy to iterate through and update in parallel if necessary. So what we do is we calculate the skinning matrix for each joint in our array, each joint in our skeleton, and then we pass that over to the renderer, and the renderer basically then converts that into a uniform array or a uniform buffer object and passes that to OpenGL. That then means all the heavy work of multiplying each of our vertices by that skinning matrix can be done on the GPU. So all the CPU has to do is update the positions of the joints, the heavy lifting's done by the GPU. So for this to all work, the entity needs to aggregate a geometry renderer component, and also now an armature component. The armature contains the skeleton. And that's done just like that. So as we have a mesh loader and an animation loader, we also have, funnily enough, a skeleton loader. And these GLTF files can also contain skeletons as well as animations and meshes and a whole bunch of other things. That gives us everything we need to render a skinned mesh. So let's have a look at that in action. So what we have here is on the left, we are rendering just the mesh. There's no skeleton. So we're taking the mesh exactly as exported by the artist. There's no skeleton. And that's what we get. He's in this kind of classic T pose. Now, the reason for that is it allows the artist to bind the vertices to the joints quite easily because the arms aren't close to the side. They're not going to get interference from the joints inside the main part of the body as opposed to just the arms. The middle guy there is loading the mesh, but also the armature. So you can see just by loading the armature in its default pose, we get a completely different setup for our robot. And then the third guy on the right-hand side is exactly the same, but we're using some nice textures that Johan made in Substance Painter for us. So just to show you the difference that using some PBR materials can make to your application realism. And you can rotate this around and it looks nice and yeah. Quite a cool little robot. So the code for that, where has it gone? So for our simple entity, we literally just have a transform, a mesh, and our metal rough material. Nothing new, nothing out of the ordinary. For the skinned entity, we just have what we saw on the slide. We also add in the armature. That's it. That's all you have to do. Now, when you use a skeleton loader, you can tell it to also create the Q joint objects on the front end to allow you to access and address those individually and animate those yourself. But if you don't explicitly request it, we only create the joints on the back end, so you're not paying that extra memory cost. That's an optimization. Oops, and sorry, back to that one for a second. And then the only difference between the simple skinned entity and the textured one is we're basically using a slightly different material, and we're telling it where to find the textures for that robot. Right, so animating a skinned mesh is absolutely really easy because we already have everything we need. The animation data just contains the transforms for the joints. We know how to render a skinned mesh. We just plug the two together, really, and it's easy. So the animator updates the skeleton poses. We send it to the renderer, and the renderer then just updates the skinning matrix palette, and we draw everything as usual. So if we do that with our little robot guy, we end up with this one. So here's our little robot friend, and he's walking along. And up here, I can just change the mode, and he can go into a run. Eventually, after a while, he goes to a sprint. There he goes, fast little guy. And then he gets tired and back to a jog again. We can make him be idle, so he's just there waiting for a fight or something. Or he can be boring you to tears with talking about animation and waving his arms around a bit like that. We can also control the playback speed. By default, they all use the same animation clock, but we can specify a clock on one or more clip animators, and then we can control the playback speed with the clock's playback rate. And all animators that have that clock set as their clock property will be affected. So this allows you to do some nice effects like keeping your UI animations running at full speed while slowing down all of your 3D animations and get some nice bullet time type effects. And I can show you that in that same example, actually. I shouldn't have closed it. Come on. So here's Mr. Walking Robot, and then I've got a little spin box up here, which if I make that go slower, we can slow him right down, and you can see the animation going in slow motion. And you can even make it go backwards. Okay, so you can do some interesting things with the clocks. So very quickly, blended animations. And we said earlier we want the animations to be composable. And one reason we want that is to avoid a combinatorial explosion in the number of animations we have to have. And we also would like to be able to transition smoothly from one animation to another and control these at runtime with user input or other application data. So some applications of animation blending is, for example, we might like to smoothly blend from a walk cycle to a run cycle. We might like to animate the head of a skeleton in different ways to the body without having to author every possible combination. We can blend from healthy to injured or transition from idle to walking. We can blend backwards and forwards with strafing motion. The use cases are endless. If you're doing the wheels of a car, you may want to blend the forward rotation with the side-to-side tilt as you turn the steering wheel. That's trivial to do with this. So let's have a quick look at the simple walking versus running case. So here's our little friend again. Let me find the controls. It always pops up right in the middle. So here he is walking along, and now I've got a slider here, which will allow me to gradually increase how much of a hurry he's in. So, oh, yeah, bit faster, and then he's in a full run. So just by controlling that one slider, which changes a single float, we can smoothly flip between walking and running and walking and running. And yep, you get the idea. And you can even slow it down as well using the clock, so you can make him run in slow motion. If you're trying to make a dramatic start for a movie or something. There we go. Where are we? Back to here. Right. Now, this is not as easy as it seems. Now, the first gotcha you're going to run into is that your animation clips may well be different durations. Okay, let's imagine you have a walk animation cycle. It takes 3 seconds to do one complete cycle. However, your run might be much faster. It may only take 2 seconds. So that becomes a bit of a pain when we're trying to blend from the walking clip to the running clip. And the blend factor, we can control either by user input, as we had on the slider just there, or it might be from some other application data. Now, to get around this problem with different length clips, what we actually do is we work in normalized time, or phase. So the phase is just a number between 0 and 1 for each clip. So it's 0 at the start of the clip and 1 at the end of the clip. However, it does require the animation to be authored such that the feet hit the ground at the same time, at the same phase in both clips. Preferably with the same foot at the same time. We had this at the weekend where Johan made me a run clip, and the run clip started on the right foot when the walk clip started on the left foot. And it looked great when he was walking, it looked great when he was running, but in between he was kind of doing this weird skippy thing like this. So you end up with some really bizarre results if you have bad data. Or some math errors. I've seen so many car wrecks of robots when I've been developing this stuff. It's weird. It looks horrible. If you're developing this stuff, don't do it with the humanoid mesh. It will make you sick. Anyway, so from the global time of our animation clock, we can calculate the phase within each clip. We calculate or evaluate the animation channels from the walk clip at phase phi, so we'll call that A phi, and we do the same thing for our running clip at its phase. And then we basically do a linear interpolation of the results. And we do that for each and every channel component for each and every joint. It's also a bit complicated to deal with missing data. So in actual fact, when I was doing this, one of the clips didn't have an animation channel for the left hand. So when I was trying to debug this to start with, the left hand was actually appearing up by his elbow somewhere. And then as I blended to running, the left hand would move down his arm. So again, slightly freaky. But anyway, we've got the indexing all sorted out now, so you don't have to worry about that. So what types of blending can we do? Well, lerp is common. That's the one we just saw, linear interpolation. But other possible types, we can have additive clip blending. So for example, if you have an animation of somebody walking, and you may have another animation clip of their head going left and right, you don't particularly want to linearly interpolate between those, we want to add them together. So that's additive blending. You can also have a generalized one-dimensional lerp. So here we just had walking versus running, but we may want to have walking versus running versus sprinting versus flat-out dead sprint, in which case you just increase one number from 0 up to whatever, and you can interpolate between all of those clips at any given time. So think of that as like being equivalent to a color gradient with the color stops, but for animations. You can do bilinear 2D lerps for doing locomotion in the plane, barocentric lerps when you have barocentric coordinates for various quantities, and then generalized versions of that as well. There's a whole bunch of stuff you could do. But we don't have to limit this to a simple single blend. We can do this in an arbitrarily complex tree. So basically, what we end up with is an animation blend tree, which represents an abstract syntax tree for animations, where the leaf nodes, the inputs to it, are the animation clips, and the controlling parameters are the blend parameters that feed into each node. And again, they can be controlled by application data. You could even have another animator animating those blend parameters. So you can really go to town on this. So this is the blend tree from that example I just showed you. So we've got the walk clip as clip A, the run clip as clip B. We set the blend factor between 0 to 1 on there, and we get the resulting clip out. Now I'll just quickly show you the code for that one, because it's actually dead easy. Blended skinned animation. And it's not that one, it's animated entity. So instead of using clip animator, we use blended clip animator. And instead of specifying a single clip, we specify the root of a blend tree. So here we have a lerp clip blend, and it has the start clip and end clip properties. Into those we feed in the clip blend values, and they are just the animation clips that you load in from file or from your application. It's as simple as that. But that tree can be as complex as you care to make it. This is a very simple one. And just wrapping up, some future work is we want to revisit the morph target animation so it can handle absolute and relative morph targets. Maybe add in some higher level helpers so that you can change between animation clips based upon a state machine, or in between animation blend trees based on a state machine. Be able to mask off channels and how they blend with existing values, extract the root motion and apply it to the actual entity rather than the skeleton's root joint. A pile more optimizations I could make, and also a graphical blend tree designer would be a really nice thing to have. So, quick summary. We have very high performance animations. We can opt into property changes, unlike the Qt Quick animations, and the artists can create the data rather than forcing the developer to do it. The developers just integrate it. And we have first-class support for skeletal animations and blend trees, playback rate support, animation blending. And just before we take questions, I will show you one final example. Oh, no, that's the wrong one. Stop, die. Sorry, I renamed it last night. There we go. So just to show you can have lots of these things, there they are dancing to Michael Jackson's Thriller. I don't have the music, unfortunately, but you can watch the dance. They're quite nice. I love the little pelvic grabs in a minute. Here we go. Come on. Here we go. Crotch grab. I'm not going to do it. Yep. And then they go back to the start again. So, any questions?
So it sounds like channels are basically just properties, right?
They map onto properties. Yes.
Okay, it's just a little confusing that you maybe could have used the same terminology like in Qt Quick, but you call them channels.
Well, the channels are the input to the property mappers, the channel mappers. The output is the property on the object. So the channel is just the raw data. What you do with that raw data is determined by the channel mapping.
Maybe one more question? Yes.
just wanted to ask, is it possible to get the source data?
For these examples?
Yes, for these
Yes, I will be
examples.
pushing all these examples to the KDAB GitHub page, hopefully to later today.
Okay, great.
Okay, so just go on GitHub, search for KDAB, and there's a repo on there called Qt3D examples. And just before everybody leaves the room, we've got some free Qt3D t-shirts down the front here, so if you want to come down, feel free to grab one in your size. They're free, help yourselves. Okay, thank you very much.